Okay, so let's say uh, you're on your bicycle. That's a sweet bike. And you're holding a ball, ping pong ball or whatever. Well, I guess something heavier than a ping pong ball, so it doesn't have much air resistance. Okay, and now the rest of the bicycle. Let's see. So, it's going to go sort of like that, that. Your foot's probably on a pedal of some kind. There's a wheel, another wheel. Are you drawing this? You probably have racing handlebars. You look pretty fit. Okay, so here's you cruising along on your bicycle. You're bald now. And you're holding this ball 1 meter above the ground. And over here is a cup. And you're riding your bike 5 meters per second this way. And you want to know, you're holding this ball exactly 1 meter above the ground. Oh, and the cup has a height of 0.15 meters. How far away from the cup you have to let go of the ball, drop the ball, for it to land in the cup? Okay, so basically, like, you know the speed that you're going to be biking along, and we're going to see if we can calculate what the horizontal distance should be between the cup and the ball when you let go of it. You know, if we calculated, you could put some tape down on the floor and do it, and get your friends at a party or something. You can do this. Any questions about the problem? Okay, so the first thing we have to do is choose time equals 0, time final, and then the coordinate system, the origin and the orientation. And time equals 0 is going to be when the ball is released. Time final is going to be when it reaches a height of 0.15 meters. And the coordinate system is going to be on the ground right beneath where the ball is dropped from. And the y-axis is going to be up. Oh, excuse me. So now we have to list out what we know and what we want. Do we know the amount of time that it's going to take for the ball to land in the cup? No. If we can do it without calculating that, that's fine. So I'll leave it out for now. Acceleration is 0 for x and negative 9.81 for y. The initial position, do we know that? Yes, because I'm writing it here. Is that what it said? 1 meter, yep. And that's the y position. The x position is 0 because being dropped from right above the origin. Do we know anything about the final position? Yeah, we know that PFY is 0.15 meters, and PFX is what we're trying to find. Do we know anything about the initial velocity? Okay, so VIX and VIY, we do know both of those, and we're going to get those because we know that at the instant it's released, the ball is moving with the velocity of the bicycle, whatever it's dropped from. And that's horizontal with a magnitude of 5 meters per second. So what are the components of that velocity vector? Positive 5, 0. So 5 for the x component, 0 for the y component. And we don't know anything about the final velocity. So this is it. Okay, is there an equation that works with this? I think the answer is no. So no equation works. So instead, let's try to find time final. Okay, so is there an equation that has time final and everything else in it is listed as known? And I think the answer is this one. PFY is equal to PIY plus VIY times TF plus 1/2 AY TF squared. So 0.15 is equal to 1 plus 0 plus 1/2 times negative 9.81 times TF squared. And so we have positive 4.905 TF squared is equal to 0.85. So TF is equal to plus or minus. Can someone calculate that? So divide 0.85 by 4.905 and then take the square root. 0.416 seconds, and we want the positive one. And now we're back to step 2, I guess. I mean, really, we still know all the stuff we did before. We're still trying to find PFX. We just know one more thing than we did before. Now we know time final. So is there an equation that has PFX in it, and everything else is either listed here or time final? And now the answer is the x component of that same equation that we just used. So PFX is equal to PIX plus VIX TF plus 1/2 AX TF squared. So PFX is equal to 0 plus, what was VIX? 5, yep, times time final. What was AX? 0, yep. And so we just have, oh, and we calculated TF. That's the whole point. So 5 times 0.416. And so that is 64. I can't do that. Okay, so PFX is 2.31808. Yeah, 08. Is that what you said? Okay, meters. So if you know you're going to be going exactly 5 meters per second and let go of the ball exactly 1 meter off the ground, put the tape on the floor 2.08 meters away from the cup, and it'll go right in. And I'm going to say this in a way that doesn't seem very like intuitive related. I'll try to connect it to the, yes. Is that the x component of directional quantities affect the y components and vice versa. This is sort of a funny wording. There's got to be a better way to say this, but I'm going to give an example that shows what I'm talking about. And vice versa. Okay, so this is what people often, seem to intuitively believe. Yes, question? Oh, well, that's true. Yeah, that's true. I think the example that I give is going to be something that people would have sort of a strong physical idea about that's wrong. But the way I say it, like, yeah, who has a strong physical idea about that? Nobody. No one's ever thought about it in that way before, really. But I didn't really know how else to say it, so that's what I'm going to talk about. Yeah, that's the example I'm going to use. So here's the truth. The motion of objects in the x direction has no bearing on the motion of objects in the y direction. Motion. Yeah. Okay, so here's the example that I'm going to use to. So this is something that, like, if you were asked, if everybody in here was asked what would happen in this example, most people in the class would get this wrong. So let's say so one person has a gun. They're squinting to aim. And this other person is holding a bullet. Okay, and they're holding them right at the same height. These people both have to be bald. This one might possibly be a monkey of some kind. And at the same instant, this guy shoots this gun horizontally, and this guy drops this bullet to the ground. Okay. Most people, if you haven't heard of this example before, you kind of have this feeling that something about the fact that it's going so fast horizontally keeps it from falling to the ground as fast. This bullet, so if you measured really carefully when these two bullets hit the ground, this one would hit the ground way before this one did. The truth is that they hit the ground at exactly the same time. The bullet just hits the ground a long way away. And I think maybe where that intuition comes from is like, if you think of what would happen in any normal space, like if I shot a bullet here, all you would see is that I basically just made a hole in the door at roughly the same height that I shot it. And you get the sense that it wasn't really falling at all. It's just going in a straight line. But the truth is, it is falling just as fast as this is. It's just going so fast horizontally that by the time it falls, you can't see it anymore. You know, by the time it hits the ground. Yep. That's right. And there are some, that's true with a bullet, and I'm going to show a video of that. There are some things where it's not true, like a frisbee, you know. And that, but when that happens, that's all air resistance, air related effects. Okay, so a frisbee stays up because of air effects. It lowers the pressure above it, and so the air pushes it up the same way like an airplane does. But if you get rid of air effects and bullets, like the air basically slows it down horizontally, but it doesn't really slow it down much vertically. And so these two, you can just do this experiment if you're careful, and they'll hit the ground at the same time. One thing that's sort of funny about this is, well, what if you have to be really careful about it, not just because you could shoot somebody. Okay, that's one reason. And also you have to make sure that they're released at the same time, and that's hard to coordinate. But you also have to make sure that this is firing exactly horizontally, because even if you just slightly raise it up or down, it'll have a drastic effect on how long it takes for this to hit the ground. And I'll do a example calculation of that after we're done with all this. You still have a question? It doesn't. I mean, I wouldn't know that ahead of time, but I know that it. Well, do all like do all guns spin the bullet, or is that? Uh-huh. But like shotguns don't spin. Okay. Well, yeah. So, anyways, what I'm going to show is with a pistol. So I guess it's spinning then, right? Because it's just a single bullet, and yeah, you might think that that does the same thing that a frisbee does. Turns out it doesn't. You know. Um, so these bullets will hit the ground at the same time. Exclamation point. Right. So let's watch this video because I know you don't believe what the math says about it. Um, see if we can identify what it is about the math that says these two are going to be the same. Okay, so let's say that both are dropped from a height of 1 meter. Or the one's fired horizontally from a height of 1 meter and the other one's dropped from 1 meter. So let's say okay, fired horizontally from 1 meter versus dropped from 1 meter. And we're going to calculate the time required to hit the ground. Okay, so let's just do the dropped one first. Okay. This is a problem that we did in 1D kinematics. So let's just do this as a 1D kinematics problem. Um, so say that this is 1 meter. That hand would have to be pretty big, but so first thing we have to do in 1D kinematics is choose a time equals 0 instant, a time final instant, a position equals 0 location, and a positive direction. What do you want to choose as time equals 0? Yep, so it's dropped. And what about time final? Yep, when it hits the ground. Zero position, you could choose this anywhere, but yeah, I think I would always choose the ground and I'd always choose the positive direction up. So that's what I'm gonna do. So these are shown in the picture. And now the second step is to figure out what we know and what we want. We're just going to go through the list. We only have those 7 variables from 1D kinematics to deal with. Do we know time final? No, that's what we're looking for. Do we know acceleration? Yeah, that's 9.81 down. So since up is positive, A is negative 9.81. I'm going to be lazy and leave out the units in this calculation. Do we know the initial position? Do we know the position of the bullet at time equals 0? Yeah, it's 1 meter in the positive direction from 0, so that's positive 1. Do we know the final position? Yep. Do we know the initial velocity? It's dropped from something that's not moving, so VI is 0. And then final velocity? Unknown, right? But we're happy without it, so I'll just leave it off. Look for one of the 3 1D kinematics equations that work here. And the one that works is PF is equal to PI plus VI TF plus 1/2 A TF squared. So we have that 0 is equal to 1 plus, since VI is equal to 0, this term is 0, plus 1/2 times negative 9.81 times TF squared. And so you get, 1/2 times negative 9.81 is negative 4.905. You can add that to both sides and you get 4.905 TF squared is equal to 1. So TF squared is equal to 1 divided by 4.905. Take the square root and you get TF is equal to plus or minus 0.455 seconds. And we have to choose, that's 2 answers. We have to choose one of those 2. So which one makes sense to us? Positive, yep. Okay, so if you start a bullet a meter above the ground and drop it, it takes 0.455 seconds for it to hit the ground. So now let's do the calculation for a bullet that's fired horizontally and see, we're going to get the same answer. Let's see if we can sort of identify how it works. So for B, this is a bullet fired horizontally at 1,000 meters per second. I don't know, that's somewhere in the right ballpark. It's a nice round number. Again, this is going to be from a height of 1 meter. Okay. And again, this starts out 1 meter above the ground. Okay, so for 2D kinematics, what's the first step? Yeah, so we're gonna do these two things again. Time equals 0 and time final, and then we have to choose an origin location and a orientation of the coordinate system. Um, time equals 0 is going to be the instant it's fired. Time final is going to be when it hits the ground. For a coordinate system, I'm going to do what I do at least most of the time, possibly all the time. I'm going to put the origin on the ground beneath where the object is at time equals 0. And I'm going to put the y-axis up. So the origin location and the coordinate system orientation are shown in the picture. And now the second step is we have to go through, now we have 13 variables we have to think about. But we go through the list of variables, figure out what we know and what we want. Do we know time final? No, that's what we're looking for. Acceleration? Yep, acceleration is straight down in free fall, and that's the negative y direction. So ax is 0. There's no component in the x direction. Ay is negative 9.81. Initial position, that's the coordinates of the bullet at time equals 0. What are the coordinates of the bullet at time equals 0? 0x, positive 1y. So pix is 0, piy is 1. Yes. Y is what? Oh, the acceleration. The acceleration is, so the acceleration vector, if you draw it, is this, right, with a magnitude of 9.81. Our coordinate system is this. So now it's just a matter of figuring out what the components of this vector are. And there's two ways you can think about it. One is, the hard way is to say it has a magnitude of 9.81. The angle is 270. So 9.81 times cosine and sine of 270 gives 0, negative 9.81. The easy way is to just notice that it's on the negative y-axis and, think about what the coordinates of the head would be. This distance is 9.81. It's in the negative direction, so 0x, negative 9.81. Do we know anything about the final position? We do know something about it. We don't know everything. We don't know how far away it's going to hit. It's going to hit a long way away. But we do know what the height is going to be when it hits the ground. What's that? 0. So P, F, Y is 0. And then the velocities. Do we know anything about the initial velocity? We can figure that out. Well, we weren't given it as components, but we were given everything we need to figure out the components. So what we have is a vector that's horizontal, and it's really long. It has a magnitude of 1,000, right? But so this is the tail of the vector. It's completely on the positive x-axis with a magnitude of 1,000. So what are the coordinates of the head of this vector? What's the x-coordinate? 1,000, positive 1,000. And what's the y-coordinate? 0. And so the velocity vector is positive 1,000 for x and 0 for y. Yep. That's a different thing. Yeah, so this is just, I mean, no, that's a different thing. Um, that's just if something's dropped. But if it's fired or thrown or whatever, then you have to account for the speed that the launch process puts in it. Um, do we know anything about the final velocity? No. So this is it. Okay, so now we have to see if they're, now we have to look through all six, question? Well, I think I mentioned this last time. I hope I did. So um, we we do in the back of our minds, I mean, hidden away in our brain, we know that the x component of the velocity isn't going to change. But don't write that down as a known, because if you do, it'll look like equations will work, but actually it'll be a dead end. So if you just pretend like you don't know anything about what the final velocity is going to be, and then any equation that looks like it's going to work will work. Okay. Um, okay, so now we have to go through all six of those constant acceleration equations. Look for one that's going to work, and I'll save you some time. The one that'll work is PFY is equal to PIY plus VIYTF plus 1/2 AYTF squared. And if you fill this in, it says 0 is equal to 1 plus VIY is 0, so plus 0, plus 1/2 times negative 9.81 times TF squared. And now if you compare this to the equation we had for the dropped case, it's the exact same equation. And the reason it's the exact same equation is since this initial velocity was completely horizontal and there was no y component of that initial velocity, we had a 0 for the initial y component of the velocity, just like we did in the case where it's just dropped from rest. Okay. So we get the same equation, and if you have the same equation, you're going to get the same time. That's the same equation as before. And so time final is equal to positive 0.455 seconds. And we saw in the video that that happens in real life too. If in reality, there'd be a small, tiny difference between these just based on the air resistance. Well, there's a lot of air resistance on a bullet because it's going really fast, but it's not going very fast vertically. And so it's being slowed down horizontally, but air resistance doesn't affect its fall time hardly at all. Okay, so key to this, the key to these two things being the same was that that bullet was fired perfectly horizontally. Okay, so let's say that now it's done a little bit sloppily and the bullet is fired angled up 1 degree. 1 degree isn't very much, you know. So how long does it take to hit the ground if it's fired 1 degree above horizontal? A height of 1 meter. Okay, so we're talking about, this is exaggerated. 1 degree is a much smaller angle than I have drawn here, but this is what we're talking about. So the bullet's shot like this, and it's 1 degree above horizontal. Terrible picture. Okay. So what was the, so yeah, 1,000 meters per second. So the thing to remember is the key to these two things being the same is that when you fired the bullet horizontally, the y component of the velocity was equal to 0. Okay? That was the thing to keep in mind. Now that it's being fired 1 degree up from horizontal, there is going to be some non-zero component for the y component of the initial velocity. And that's going to affect the time that it takes to hit the ground. Okay, so we have to choose these. Time equals 0 is when it's fired. Time final is when it hits the ground. Our origin location is on the ground, right beneath the bullet at time equals 0. And the coordinate system is the y-axis up, x horizontal in the direction of the shot. That's all just like I did before. And now let's go through the variables. Time final is what we're trying to find. Acceleration. This is free fall. Our y-axis is up, so the x component is 0. The y component is negative 9.81. The initial position, pix is 0. piy is positive 1. The final position, pfy, is equal to 0, and we don't know how far away it's going to hit. The initial velocity we can figure out, but we're going to have to calculate that. So to calculate that, here's the coordinate system. Here's the initial velocity vector. Then again, I'm really exaggerating that angle. This angle is 1 degree, which is way, way smaller than that. That's probably more like 15 degrees. It has a magnitude of 1,000. So that initial velocity vector is 1,000 times, to go counterclockwise from the x-axis, you go 1 degree. So 1,000 times the cosine of 1 degree, 1,000 times the sine of 1 degree. And that comes out to be, so this one is, the horizontal one is basically 1,000. I think you get 999.884. Okay. Like we saw before, to figure out the time, we're only going to use the y component anyway, so this won't come into it. But then what's the y component? Okay, so remember, the reason, so the x component is 999.85, and the y component is 17.45. The reason that if you fired the bullet horizontally, it hit the ground at the same time as if you dropped it, is that the y component of the initial velocity when you drop it was 0. Look at how big it is now. Even though that angle is tiny, 1,000 meters per second is so fast that this has an initial y velocity of 17.45 meters per second. That's like almost 40 miles an hour. So this bullet is going to vertically, like if all you saw is like the vertical shadow of what it's doing, its vertical motion is going to be the same as if you launch something up into the air at 40 miles an hour. That's how long it's going to take for it to go up and come back down. So it's going to go up, what I can't remember the number, but say 15 meters, you know, it's going to go up 40 feet in the air or something before it turns back around and hits the ground. So let's calculate the time. At that speed. That's exactly right. Because again, that x and y motion, they don't care about each other. It's just a matter of the y motions. So we'll use the same equation. Pfy is equal to Piy plus Viy Pf plus 1/2 Ay Tf squared. So we have 0 is equal to 1 plus, this time we have 17.45 Tf minus 4.905 Tf squared. And I'm going to rewrite this as a hint of how to solve this. So negative 4.905 Tf squared plus 17.45 Tf plus 1. Yep, how do you solve this? Quadratic formula. And I don't remember if I mentioned this last class, but anybody who has a TI graphing calculator, if you come talk to me at lab sometime when I'm not busy doing something else, it takes 30 seconds for me to put a program in your calculator that does the quadratic formula, then you never have to think about it again. Look at how busy Grace is thinking about it. Okay. Oh, you're awake, just in time. Okay, so this is A. Negative 4.905 is A. Positive 17.45 is B. 1 is C. Plug that into the quadratic formula, and TF is equal to negative B plus or minus square root of B squared minus 4AC divided by 2A. And you get, I forget what the negative 1 is, but we don't care about negative 1s. There's a negative 1. I don't remember what it is. 0. That's the one we don't care about. And then the other one is 3.62. Look at it, it's spreading along the row. Everybody down there, be ready to fall asleep soon. Okay, so 3.62 seconds. So remember, when the bullet was fired horizontally, it took 0.45 seconds to hit the ground. Now, because you were inaccurate in doing it horizontally and you lifted it up 1 degree, probably that much, it takes over 3.5 seconds to hit the ground because it goes way up in the air before it gets to its highest point and then starts falling back down.